Back. I did spend a couple of years retired before I joined Untitled Magic, but it's nice to be back into the conference circuit. Last time I was here in EMEA, IDUG was 4 years ago in Dublin, so it's been a long time coming back. And I've had a rough weekend so far, starting with a rail strike in Paris on Friday. It was a nightmare. Almost lost my passport, left it on the train coming here, and grabbed it just in time before the train was leaving. And I didn't get a good night's sleep last night, so it's been a rough week. Anyway, so I selected this topic because I don't know if you guys know Jeff Jostyn. He was a data sharing DB2 data sharing architect going back to the 90s. And I joined DB2 in 2000, and Jeff and a lot of other people from the lab would do all these presentations about data sharing. Now, I looked at the IDUG database to see when's the last time somebody did a presentation on data sharing, and it was by Jeff 10 years ago. So it's been a long time, and anybody's been talking about data sharing. IBM just seems to have forgotten about it. It like assumes that everybody knows about it. And of course, it's one of the best things about ZOS. Probably one of the most important things that's kept it alive, that plus top security, the best security in the system, in the industry, I mean, and made perhaps the best performance in the industry. But data sharing, which was invented in the mid-90s, has really made, distinguished DB2 in terms of availability better than any other platform. Now, when I would listen to Jeff's presentations, I could understand what he was saying, but I would always forget it within a week, because it was so complicated, and it was more like IBM's internal view of it looking outward. And today, I'm going to try and give you more of an outward view looking in. And when you're looking at it that way from the outside in, you're looking at instrumentation that DB2 provides and trying to manage the system, interpreting what's going on from the instrumentation. So I'm going to talk about metrics that are within DB2 that help you to give you a view of what's going on and what you might do to manage the system based on those metrics and what sort of corrective actions you might do. Now, for the most part, DB2 is self-managing. So there really isn't very difficult to manage it. But there are a few tips to keep in mind as we go along. So I'm going to be talking about member-level constraints. According to the data sharing group, we have several members that are all sharing the same database. I'm going to talk about how we identify locking and latching contention things that affect response time, contention events. And I'm going to talk about caching using the group buffer pool. Specifically, I'll especially be talking about write caching, because today, as it turns out, most people are only using it as a write cache. So why do we do DB2 data sharing? One is, of course, for capacity reasons. One data member within a data sharing group, or one DB2 subsystem without data sharing, is limited to a single LPAR. And so you're limited to the size of that LPAR. So once you've outgrown the size of that LPAR, you would need to expand to get more CPU power or more memory, or whatever. And also, even more important perhaps, is that you need it for higher availability. If you have two members and you want to upgrade to a new version of DB2, you want to apply maintenance, or one member goes down due to an unplanned outage, then you would have an outage unless you have another member in which you can shift the work to. Now, hopefully, you have enough capacity on that other member to sustain an outage on the one member. And that's one reason why you might want to have more than two members in one data sharing group, just to increase the amount of power you have when you have one member go down. So that's what allows for easier growth accommodation. And it's scalable and non-disruptive. I don't know that much about Oracle and the other relational databases, but everybody says they're not scalable. So I take them for that word. At least the IBMers say that. I don't know what Oracle says about that. But, and we also have algorithms to make sure that the work gets dynamically spread across the sysplex. And also allows for system consolidation for easier systems management. In the case of Oracle, they might have to split the databases into multiple database environments, and makes things more complicated. So this is a chart from Jeff's presentation, which I borrowed, which illustrates a sysplex. And there's a sysplex timers, which is really kind of transparent to me. There isn't really any instrumentation involved in that. There's 3 structures in the coupling facility that are shared across all the systems. So we have the group buffer pools. We have the SCA, which is the system communications area. The SCA is pretty much transparent to me because I don't see any instrumentation involving that. And then there's these lock structures, 1 per member. Oh, well, not one per system. No, so it's 1 per data sharing group. I'm sorry. And that, of course, is a backup. Uh-oh. Now I'm nervous because Akiko's in the room. And she... I better say everything correctly now. Akiko and I used to work together. Anyway. So here's an example with a bunch of different DB2 subsystems all running, and well, they could be running on different LPARs. They don't have to be. You could also actually have multiple data sharing groups running on the same LPARs. And they all have their own local buffer pools. Now that's where we want to do our read caching, to have large amounts of memory in each LPAR and hopefully get buffer hits in the local buffer pool rather than going back up to the group buffer pool to read the data. And they're all sharing the same DASI, but they all have the same DB2 catalog and the same databases. So workload balancing is important, and it's one of the things you can monitor to make sure that the work is being evenly distributed as much as possible. So you can monitor various metrics, such as the number of transactions that are running, the number of get pages. I love get pages. It's so easy to monitor, and it's a really good indication of how much work is being done. So you want those spread across your members. But, of course, sometimes you have batch jobs running. In a batch window, you have a lot of batch jobs running. An individual batch job, which could be doing a lot of work, is only running on an individual member. And it's not that easy to make sure that the batch jobs are evenly spread across the sysplex. So when the batch jobs are running, it tends to cause a more uneven distribution. And of course, when I say even distribution, I mean if the size of each processor is the same, with the same processing power and same amount of memory and so on and so forth. If you have an unbalanced configuration, you might expect an unbalanced distribution of work. So here's a get page chart, a graph that shows a particular customer that happens to have 13 members in one data sharing group, which is a bit excessive. I have not seen one higher than that, not even close. This guy, DBHG, though, he's really not doing anything. He's only there for IDAA. He's reading logs from each of the other 12 members and replicating the log records to IDAA. And hopefully, Akiko will make that go away so that we wouldn't need it anymore. Anyway, and you'll notice, though, okay, this is a 24-hour period. I think it is. This is back on February 4th, February 5th. Yeah, so I started at about 6 a.m. and went to 6 a.m. So you notice this is the daytime over here. And you notice how the get pages slowly increase during the morning, and it reaches a peak around noon. And then it settles back to down at 5 o'clock, and that's when the batch window starts. And then all hell breaks loose, and you get 1 million get pages, and they're all over the system. But during the day, there's really only 6 members that are doing a lot of work. The other 6 are not doing very much. And I wonder if anybody can guess why that is. No. Well, why would you know? Those 6 members is where CICS are running. And so the customer has chosen to limit CICS to those 6 members. And this is a very heavy CICS user. So I don't know why they chose to do that, but that was their choice. So I don't know what the other 6 members, what their purpose in life is, except that during the batch windows, they start running batch jobs and doing a lot of work. There is also some DDF work in the system. And I haven't really checked lately, but I suspect that this low level of work during the day is probably coming from distributed. So these are some of the member level constraints that you could have that would limit how much work you could do on an individual member or in the data sharing group. The log latch is probably the most important of the latches. And that's just that's a latch that's associated with each member. So each member has its own log latch. And there's only one latch per member. So, and logs themselves could potentially be a constraint. The I/O could be a constraint. But I've yet to see it because our devices are so fast these days. And I haven't seen anybody really stress the logs that much, especially now that we have Z hyperwrite. That helps a lot with logging as well. And when we're doing using Metro Mirror. But not all latches. So some latches, if you have a latch constraint, such as the log latch, you could, now we've done a lot in DB2 to relieve those constraints, but in the old days, it was more likely you'd have that contention. And the only way you could overcome that constraint is, well, one way is to reduce the amount of logging that you do, which means doing less work, essentially. Or you have to split the work onto other members. So then you have to create more horizontal growth in your data sharing group. But there's lots of other latches that, well, I guess even the buffer pool latches, like LRU latches, again, if you're too bottlenecked on one buffer pool, I guess you could spread the work across multiple buffer pools. Or you could split the members, or excuse me, the DB2 objects into different buffer pools. So you'd have to require more buffer pools in order to have more latches, and you could do that within a single member. Log I/O throughput capacity, as I was saying before, I've never seen anybody have a log I/O capacity constraint, at least with one member. One thing I should mention about logs is that one of the downsides of having lots of members is when you're in a recovery situation. Because then when you're recovering a DB2 object, the recovery utility has to read the logs from all the members and merge all the log records. So the more logs you have to merge, the more work it has to do, and maybe it's a little bit slower. I measured it a long time ago, but it only were like 2 members, so I don't know how it scales as you add more members. And again, there's so many it depends factors that affect the performance of recovery that it's too complicated to try and analyze. Virtual storage used to be the most important constraint in the system before we had 64-bit. So now that we have 64-bit virtual addressing, that's no longer a problem. Do as much work as you want on a single member without running out of virtual storage. And in the old days, if you ran out of virtual storage, you crashed your DB2 subsystem. So that was a really bad problem. It wasn't a performance issue, it was an availability issue. So how many members do you need? Well, basically enough to achieve the level of availability and good performance when you do have an outage. If you only have 2 members and one goes down, you're losing half of your capacity. If you have 3 members and one goes down, you're only losing a third. So it's up to you as to how much capacity you're willing to get along with. And you need enough to avoid latch contention. But only really a few are needed. And as I said, as I showed you before, one customer had 13 members, which is a bit excessive. Most people, I think, have 2, right, Kiko? Most people only have 2 members. 4? Oh, most people, she says most people have 4. Okay. 3? Do I hear 5? No. Okay. So what's the downside of having more members? Well, it's more to manage. And for me, it's just more data to have to look at. Whether I don't know if that's a problem managing it or not, but it annoys me to have to look at more data. Now here's just a report that shows you the response time components, the class 3 suspension time components. And I wanted to point out some of them that are related to contention. Usually the number one effect on class 3 response time, actually, is this including CPU time? No, it's not. CPU time is missing here. So it's just class 3, which is all the suspensions. So the number one suspension time category is usually synchronous I/O. The second one, I'm not sure which one's here, but the second one I typically see is log I/O or other write I/O. suspension. Other write I/O is associated with prefetch, which is almost inevitably dynamic prefetch. And we also have latch constraints and locking constraints. So latching, now if this was on a browser, I could actually hover over these bars and figure out what the category was. Using the colors is sometimes difficult. So it's a lot easier on a browser. Anyway, we got latch. I think latch is pretty small over here. I don't know where it is. But these ones that I highlighted in here, the global contention is associated with data sharing. And also the lock claims and drains are kind of associated with serialization. And Akiko may notice that we're actually missing one category of global latch constraints. But most people actually don't. This, by the way, is an expanded set of suspension categories. In a lot of cases or a lot of products, we'll just collapse all these global contention events into one because it's easier to look at it that way. And then if you wanted to drill down, you could then split that one category into like 5 or 6 categories. I'm only showing 5 here, but there really should be 6. And I'm not even sure. I mean, who cares about which category it is? To me, it's just all lock contention. And the solutions that you would deal with each one, for me, is the same. And I'll try to talk about that. So now I'm going to talk about monitoring. Okay, pretty much the same as when you're not doing data sharing. You want to collect SMF 100, in which case we have statistics by GBP for each member, each group buffer pool. And in SMF 101s, we have statistics also by GBP, but for each transaction. And what I've discovered, at least with this customer that had 12 or 13 data sharing members, is there's an awful lot of data when you, and they have, by the way, I don't know how many charts, they have like 30 4K buffer pools. DB2 supports up to 50, and you probably only need like 4, and they had 30. That's 30 sets of statistics for each member, and they have 12, 13 members. That's a huge amount of data to manage. So I would not recommend anybody to have 30 4K buffer pools. They really should consolidate them. And then there's some key performance metrics about locking and caching, mostly that are related to health checks. Now, health checks are a different kind of metric to me than performance metrics. With the health checks, either the health is good or it's bad. It's like black and white. But then there's a lot of other metrics that are more like gray areas. But with locking, it's more black and white, I'd say. Unless you're looking at class 3 suspension and you see, oh, I got this much lock contention. And you want to know, out of 100 milliseconds of response time, what percentage of that is lock contention. It's not an absolute number that I care about. It's the percentage. So it's really better to look at the accounting information and the response time to understand whether or not locking is a problem. And then there's among the health checks, there's two errors that you could possibly have, and that's if you've got like a failure with one of your coupling facilities when you're doing duplexing. So there's one metric for whether or not the primary has failed, another one whether the secondary has failed, or that it's full. That's what they call them. And then there's the directory reclaims. Now with directory reclaims, there's 3 ways to get the data. There's ifkids 230s. I didn't mention 256 here, but I think they're in 256 as well. But you don't have to collect those if you're collecting Rmf data, because Rmf also has the directory reclaims. And it turns out the DB2 is not measuring the directory reclaims itself. It's getting that data from the system. Who's getting it from ZOS, I mean, and ZOS is getting it from the coupling facility. And so we got these lock statistics. You have them by member, and there's some set of statistics that are by buffer pool, group buffer pool, the p-lock statistics. But most monitoring tools, I think, summarize the p-lock statistics at the member level, and then you can drill down for if you have contention on p-locks. I'll be explaining what p-locks and l-locks are in a second. Let's see. And then there's let's see. You got statistics about the number of lock requests and the number of unlock requests and the number of lock suspensions. If you compare the number of lock requests versus unlock requests, that tells you a little bit about how many locks each transaction is doing. When you do under a transaction, under a commit scope, you'll be getting a series of locks potentially, and then when you do the commit, that's when the unlock occurs, and the one unlock request will free up all the locks that were obtained under that commit scope. So you tend to see a lot more lock requests than unlock requests. That's what that's all about. And then there's some health checks that are collected by Data Manager, which talk about deadlocks and timeouts. Those are really serious problems that are going to affect performance. Not just performance, but if you get a timeout, it means you didn't get your work done. So it's kind of a failure, and you've got to do something to deal with that. And then there's lock escalation, which is, I'd say it's a performance issue, and false contention, which is also a performance issue. We recommend, as always, to collect the statistics classes 1, 3, and 4. These include statistics for timeouts, deadlocks, and suspensions. Class 3 also includes IFKID 172, which gives you information about deadlocks, and 196 gives you information about timeouts. And of course, with reclaims, it's IFKID 230 and 254, or RMF. And then in accounting classes 1, 2, and 3, that'll give you IRLM, suspension, and global contention. And if locking is increasing the elapsed time of your transactions or batch work, then you would investigate further. So now I'm going to spend a few minutes talking about locking, and then I'll finish up with group buffer pools. So these are the potential locking problems. We have deadlocks and resource timeouts. We have real contention and then false contention, which is, and you want to be able to distinguish between the two. Real contention means it's a characteristic of your workload, and there's really not much DB2 itself can do about it to avoid those contentions. But false contention is really because your lock structure is too small. And I don't want to explain what false contention is. I just want to say that the bigger your lock structure is, the less false contention there will be. So you want a small amount of false contention as a percentage of all of your contention. Lock escalation is something to be avoided. I guess I have a chart on that later, so I'll talk about that later. Now, DB2 has algorithms to try and avoid getting locks, but there's some things that can happen that reduces the effectiveness of DB2 lock avoidance, and there's a metric on that too that talks about how many times it failed to work. But there's not much you can do actually to avoid it, I guess. I don't think. Actually, there is, and that's get fewer locks. Now, there's L locks and P locks. L locks, what's the difference? L locks are being gotten by the system whether you're using data sharing or not. And the L stands for logical locks. When you're doing row-level locking or page-level locking, that's referring to L locks. And P locks are about buffer coherency. It's not about trying to serialize the data. Now, buffer coherency is a term that IBM coins, and I can never remember exactly what it means, but I translate it into my head as meaning trying to avoid data corruption or a data integrity problem. If you have two different members, they're trying to update the same page, and so one updates the page, and then the other one, if the other one were to update it again and wipe out the other member's changes, you lost some data. So the P locks are all about trying to avoid that. And when a P lock it's obtained on behalf of a member, it does not block any requests, any SQL activity on that member. So every transaction that's running on that member shares the same P lock. And if you're not using data sharing, there's no such thing as P locks. You don't have any P locks at all. When we talk about deadlocks and timeouts and lock escalation and lock avoidance problems, those are all related to L-locks. Now, why am I even talking about L-locks if it's not related to data sharing? Well, as it turns out, the two are kind of related in the sense that when you have P-lock contention, it has a cascading effect on L-lock contention. And that's why you end up with more L-lock contention in a data sharing environment. So there's like one contention, one resource causes contention on another resource, in a sense. Claims and drains are something that most of us forget as to what it means, so I always have to go back to the definition myself. A transaction makes a claim against a page set when it has a read-write interest. So as soon as, basically, when the transaction starts and it refers to a page set, it gets a claim. And that claim is held until commit time. That frees the claim. So when a utility needs to grab hold of a page set, let's say it's online reorg, and he needs to switch from the current active data set to the shadow data set at the end of the reorg, he has to obtain a drain. And when he obtains that drain, or attempts to obtain the drain, all new claims are blocked. So no new transactions can begin. But the transactions who hold a claim will continue to run. And they will run until they do a commit. When they do a commit, they free the claims, and then they might try and do more work, but they have to reacquire the claim, and they're going to be blocked by the utility. And this can go on, take a long time before the utility can actually obtain the claim. And it's possible that he'll never be able to obtain the claim. There's certain utility parameters that allow you to control this processing. But if he fails to obtain it, then the utility will fail. So you have to set the parameters as a trade-off as to being able to get those reorgs to run, or whatever utility that's trying to obtain the claim, and your online transactions who are constantly trying to get these claims. So page level locking versus row level locking. This, of course, is one of the parameters you could set at the table space level. Row level locking is what you want to do if you want to maximize concurrency. But it also has the downside of potentially increasing the number of deadlocks that you have. And for sequential access, row level locking also has the effect of increasing CPU time. Because if, let's say, you have 20 rows per page and you're going to process all 20 rows, if you only get one lock per page, as with page level locking, that's 1/20th as many locks as you would if you were doing row level locking, getting 20 locks for that same page. So for sequential, it's much better to do page level locking. Now, page level locking provides less concurrency than row level locking. So that's, again, it's the downside of page level locking. And since data sharing is always using page P-locks, row level locking does not add to the risk of deadlocks unless the conflict is with an individual member. Or in other words, global contention will prevent the deadlock that would have occurred without data sharing anyway. So with P-lock statistics, that's when we start dealing with contention that can be either real or false. And we have statistics on those. And IBM has rules of thumb about what the percentage of real contention, what percentage of the overall contention should be false, or it should be no more than that. And I believe the guideline is 3 to 5%. So if it's above 5%, that's really bad. If it's between 3 and 5%, they say, be careful. It's kind of in the gray area. You might want to be concerned about that. And less than 3% is fine. But who can remember these rules of thumb? And who wants to calculate the percentage when you're looking at all this data? Wouldn't it be nice if your monitoring tool does it all for you and flags it and does it for all the members at the same time and all the, Well, it's at the member level, not at the group buffer pool level. So it's still a lot of data to have to monitor all day long, every day. So it's nice to have some tools that'll do that. Oh, actually, I said 3 to 5%. The chart says 1 to 3. See, I get it wrong. I need to read my own chart. 1 to 3%. Nobody could remember. And then another set of statistics has to do with PLOC negotiations. I don't even want to explain what PLOC negotiations are. Just know that there's some statistics, and it costs a lot of CPU time when there's contention to resolve these PLOC constraints between members. So that's all done automatically by the system. But again, there's IBM guidelines that the number of PLOC negotiations should be at most 3 to 5% of the total number of XCS IRLM requests, which are measured. And again, you want your monitoring product or tool to calculate these things for you and to flag them when you've gone above these rules of thumb. See this complicated formula that IBM tells you in its presentations? Do you want to be having to calculate these things and knowing the names of those fields to look at? It would be a real pain. So, but the PLOC negotiations, now these are really important to run, to have top priority in your system. They're running in the DBM1 address space. And I remember one time we tried to have those run on the zips, discovered if you had zip constraints, performance wasn't too good because we weren't resolving these PLOC contentions efficiently. So these are like the most important SRBs in the system to run. Because it can be, when you have PLOC contention, you're not just affecting that one member. You're affecting the whole data sharing group. It's really big. So that's the reason why you want your DBM1 address space, or one of the reasons at least, to have the highest priority of execution, of dispatching in the system. Now we have PLOC negotiation statistics for each GBP. And typically they'll get summarized at the member level. So only when you're trying to diagnose why you got PLOC negotiations, you have to actually drill down into at the group buffer pool level. And one of the reasons for drilling down is there's 3 types of PLOCs that DB2 categorizes them. One is index page PLOCs, another was data page PLOCs, which are related to the tables themselves, and space map page PLOCs. So these are the number of locks, block contention, I think, events, right? And then there's a number of PLOC negotiations. But it's really the categorization that I like, the fact that you can identify as related indexes, tables, or space page PLOCs. And the reason why I want to know that is because the solution varies depending on what type of PLOC it is. What if you got index page PLOCs? Well, this says it's most likely due to index splits. So how would you avoid the lock contention? Avoid the index splits. I'm not going to talk about the details of how you avoid index splits, but one of the things you can do is increase the page size of your indexes. Data page PLOCs, most of the time there's not much you can do about it, but the more rows you have on a page, the more likely it is you're going to have PLOC contention on it. So if you divide your rows up into lots of pages, in the extreme case, you set a max rows to 1, in which case we only store 1 row per page. That would help greatly to reduce the amount of data page PLOCs. That's okay if the table is really small, but if you've got a really large table space, using max rows of 1 is just not practical because you'd be using so much DASD storage. Space page map PLOCs, that's pretty easy to avoid, and that's by using member cluster. And in my opinion, you should probably always be using member cluster, depending on what kind of diode devices you have, I guess. But with IBM devices, I probably would recommend always using member cluster. The downside of member cluster, I see Bart shaking his head. So somebody disagrees with me. But, maybe Bart can say why he doesn't like member cluster.
The interprocessing is okay, but after rest we have maybe update or delete processing.
Pardon?
Inside processing is okay in a cluster, but afterwards maybe delete or update processing.
Because you lost clustering? Because, yeah, your cluster ratio is going to go down.
Yes,
Yeah. That's the downside. You're going to lose a high cluster ratio. If you've got solid-state disks, though, random I/O or in hyperlinks makes it even better. Random I/O doesn't cost you as much as it would otherwise. So if you go with the absolute latest technology, certainly, I don't think the impact of losing clustering is as great as it used to be. Also, when you're using list prefetch, IBM implemented list prefetch optimizer in the year 2012. It's been 7 years. And if you don't have a control unit that supports list prefetch optimizer, I suggest you get a new IBM control unit. And Hitachi's fine too. There's a third vendor that doesn't have it, so I won't mention it by name. I recommend either IBM or Hitachi for your storage, in which case you can use member cluster and avoid these contention problems, probably. Okay, so here's a typical report showing page p-lock suspension, sum for all GPPs. I don't want to give a plug for my company, IntelliMagic, but this is from IntelliMagic Vision, so are all my other charts. So this shows you, well, the yellow is the biggest category, so most of them are related to indexes. The second most common category is the data, and in this case, we don't really have that much in the way of space map page p-lock suspensions. Okay, so here's member cluster. So voice the p-lock contention on the data pages and the space map pages. One of IBM's recommendations is do not use lock size row without member cluster when inserting at the end of the table. I'm not sure why, but I just refer to that statement and obey it. The disadvantage is that you'll use more DASD space because the data is going to tend to get spread more across more pages, and it sacrifices the clustering sequence with respect to the cluster key. By the way, if you're doing index access and you're not using the cluster key, then it doesn't matter if the cluster ratio of the cluster key, index is high or not, because you're not using that index. And anyway, you can always use reorg to reclaim space and to restore the clustering. So yeah, if you're using member clustering, then maybe you have to use reorg a little more often. Another thing to be aware of for controlling the amount of lock contention that you have is the isolation parameter and the current data parameter. Isolation parameter has 4 possible settings. UR, which is uncommitted reads, CS, which is cursor stability, and that's the default. RS, which is read stability, and RR is repeatable reads. RR does the most locking. It's the absolute worst. It's a very aggressive kind of locking. RS also gets a lot of locks, but not as much as RR. But the default, which is CS, it'll get 1 lock at a time per transaction per object. So as soon as it wants to get another lock, it frees the previous lock. And that's why its performance is usually pretty good with CS. And in my experience in the last couple of years, everything I've seen is using the default, either the default or UR. Most of them are just using the default. So I haven't seen any uses of RS and RR. But you really want to be careful about using RS and RR because those can cause problems. Track mod no. That's related to space map pages performance. Whenever you modify a page, if you're using track mod, yes. Every time you modify a page, we have to set a bit in the space map page that indicates that a particular page has been modified. And that's used by incremental copy. When we want to find for the utility, it wants to find all the modified pages and write it to the image copy data set. If you're not using incremental copy, there's no reason to use track mod yes. And if you happen to have space map contention one of your options is to stop using incremental copy, I guess, because there are other types of copy that you can use, full image copies, or flash copy, or use the backup utility, which uses flash copy at the volume level, and so on. Deadlock content detection and resource timeouts. There's a lot of controls that you have, and I'm not going to discuss them all. I just referred to this old red book, DB29 for ZOS. Don't worry, it's version 9. It hasn't changed, I don't think. If you can find a more recent one, great. But this will do good. I think this red book will do good to, you want to review all the options you have on controlling deadlocks and timeouts. I don't know if I have a chart on it, but if you actually get down to the point where you got a lot of lock intention and you want to know what you're locking, I would punt to IBM, open a PMR, and they'll tell you what traces to collect, and you can send your traces to them. I'm certainly not going to explain to anybody how to analyze lock traces. And I used to punt all the time to Akira Shibamiya. So unfortunately, it doesn't work for IBM anymore, but maybe now I'll get punted to Akiko. And so, and these are the locking health checks get summarized. I've mentioned them before, but this is just for one data sharing group. You might have several. The customer I was showing you before actually they've had more than 6 data sharing groups in the past. They seem to be coming and going. Right now they have 6 different data sharing groups, but I'm only showing the one production data sharing group here. And it shows in green those metrics that are not having any problem. And then we have symbols that are in red to show potential problems. And these are not real problems necessarily, but there's always some contention at this customer. I have an analogy about lock contention. Now that I'm 65 years old and I have to go to the doctor and he tells me every year I have high cholesterol. Now, and then he tells me I should take statins. And I can choose to ignore him. And it's just part of getting old. Well, lock contention to a certain extent in data sharing is just normal. You can't, don't try to fight it. It's just always going to be there to a certain extent. You want to look for spikes, and when it gets too abnormal, and then that's a real problem. But sometimes it'll get flagged just because you have this chronic low-level amount of contention all the time. And I would say don't worry about it. P-lock negotiations, I would worry about those more, I think. This one's flagging global lock contention. I wouldn't worry too much about that. But I'd look at it at least once. And then you can set the thresholds, too, to stop these things from getting flagged if you think it's being too sensitive. So investigating locking problems, so use accounting trace to monitor locks, find out which particular applications are doing the locking and address those. Maybe you find out through this which ones are using isolation RS or RR, and you might want to get those changed if you can, or have them run, actually moving them out of different members is not going to help. And lastly, if all else fails, use get performance traces and send them to IBM. Send them to BART. Okay, I have 15 minutes left, I think. So now I'm going to talk about group buffer pools, mostly about write caching. There's this GBP cache parameter that IBM created back in 1994 when data sharing was invented. Some of the values you can set it to are changed, in which case only the modified pages are written to the group buffer pool. If you set it to all, we're going to write clean pages into the buffer pool. And back in the 1990s, IBM didn't know what the future technology of storage was going to be, real memory, And I think, at the time we had expanded storage. The storage that's in the group buffer pool is not byte addressable. It's only page addressable. And IBM used to have a kind of, it was called expanded storage, that was cheaper memory than real memory. It just wasn't, it was cheaper because it wasn't byte addressable. And that's kind of basically what's in the group buffer pool, because we're never actually addressing individual bytes within the group buffer pool. All we're doing with the group buffer pool is moving massive amounts of data. Basically, if it's a 4K page, we're moving 4K back and forth between the local buffer pool and the group buffer pool. And when we're doing cast outs, we have to read it back, not into the buffer pool, but into a work area. And you can't do I/O in and out of a group buffer pool. So in order to actually, well, when it's a modified page, we'll copy the data first from the local buffer pool into the group buffer pool, and then later we'll asynchronously do cast out, in which case we read it back into a work area, and then write it out to DASD, doing cast out processing. Okay, so we want to, nowadays though, we want to do all our read caching in local memory, which has gotten much cheaper than it used to be in the old days. You don't need to have a huge group buffer pool to support that, the large local buffer pool. But we're going to try and get high local buffer pool hit ratios. And we're not going to try and get hits in the group buffer pool. If we do happen to get read hits in the group buffer pool, it's just by chance. And it doesn't really, it's not important what the percentage of group buffer pool hits is. And the only reason you got a hit there is probably because some other member just happened to have modified it recently. But it probably will, it's going to age out relatively quickly from the group buffer pool before any other members will get hits over there. But also the larger the local buffer pools are, the larger the group buffer pool needs to be. And that's in order to maintain buffer coherency across the different members. So we recommend using the default of changed, except for large objects. And in that case, IBM recommends to use GBP cache equals none for lobs, because the likelihood of actually actively sharing the same lob across members is low. And so we figure we might as well just write a changed lob or a new lob. Usually they're new. Just write it directly to DASD. And don't bother writing it into the group buffer pool. And never use GBP cache at all. And I think I'm going to be talking about that later, so I'll continue on. Typically, people do use GBP cache equals changed. And then deferred writes, which are called asynchronous writes. They are asynchronous with respect to the allied threads. They may write around the GBP, but the commits synchronously cannot. The commits are always synchronously writing into the GBP. This GBP write around I'm going to talk about later. This was a new algorithm that was introduced in version 11. And this was really important in improving the performance of group buffer pools. First, we have this concept of GBP dependencies. When multiple DB2 members have a read-write interest in an object, the get pages are counted as GBP-dependent get pages. So you would go to the group buffer pool statistics to see that. And most of the time, almost all, especially that example where I had 12 data sharing members and CICS was running on 6 of them, almost all the get pages are GBP-dependent. And in the old days, IBM used to try to recommend that you should avoid GBP dependencies if you could. But especially with that many members, it's impossible to avoid GBP dependencies. So just let it happen and don't worry about it. You will see, however, that when online reorg is running and he's writing into, say, a shadow data set, or the load utility using load replace, if he's creating a brand new page set, loading it from a flat file, he gets exclusive access to the table or table space. And in that case, there's no GBP dependency. So when I'm looking at the data and I see a lot of get pages that are not GBP dependent, for me, that's a good clue that it's probably utility running, namely online reorg. It's all about being Sherlock Holmes, looking at the data, trying to pick up clues from it to figure out what's running. Let's see, typical exceptions, utilities, and also, now we have these internally DB2 has these read no get pages, which none of the IBM presentations ever talk about. These read no get pages are stealing buffers, but they don't care about the contents of the buffer. It's just a brand new page, essentially, that had no data in it before. And so these are not, well, we're never going to get PLOC contentions on it because no other system is using it. I think they still get counted as, well, I don't think we get a GBP dependent get page being incremented for that. Now, the cross invalidations, IBM presentations talk a lot about cross invalidations. This is what we get when, let's say you have a buffer in member A, in the local buffer pool of member A, and member B also has a copy of that page in its local buffer pool, but if member B updates it, updates the page, and then, well, he'll then set a bit in the directory of the GVP to say that it's been modified. That's going to invalidate the copy of the page on member A and all the other members. So that's what causes cross invalidation. So the more updates you have, the more cross invalidations you have. Is it a problem? No, it's just the cost of doing data sharing. There's not much you can do about it. So just accept it. You're going to get a lot of these cross invalidations. Now we also have to divide up those cross invalidations into hits and misses. So let's say, I'll go back to member A. Let's say he had it in his local buffer pool. Then he's going to, but it got invalidated. So then he's going to go search the group buffer pool to see if it's there. And if it's there, it's counted as a hit. If it's not there, it's counted as a miss. But there's nothing you can do about it anyway, so you can choose to ignore those statistics. They're not really all that interesting. Just indicates whether or not it was recently modified. And this kind of, it tells you in which, these are, 4 or 5 different categories of get page statistics that they have. Some of them result in a sync IO, and some of them result in no IO, if you really want to know. But the more important statistic, I think, that you want to modify or monitor, because it's really an indicator of a potential problem, and that's directory reclaims. If the GBP cache is undersized for the aggregate size of all of your local buffers, then it means your directory, is too small, and that's going to cause cross invalidations, which could then cause more sync IOs. So IBM, basically, its rules of thumb are look for cross invalidations. If you have any at all, that's considered a problem, and the solution is increase the size of your group buffer pool. However, and here's the reality. Go back to my cholesterol analogy. Just because you have high cholesterol doesn't mean you're going to die. This is the doctor's recommendation. And you can choose to ignore it or not. If you really look at you can go analyze and see whether or not your cross invalidations are causing more sync IOs or not. If you don't think it's causing more sync IOs, perhaps because there's no correlation between buffer directory reclaims and sync IOs, then don't worry about it. And I think there's a reason why this tends not to be a problem. And let me see if I can explain that in terms of page residency time. Let's say your local buffer pools are huge, and your page residency time is 30 minutes, which is a pretty healthy page residency time. But your directory reclaims, the directory entries also have a certain page, I shouldn't call them page residency, but a directory entry residency time. That time might be 10 minutes, let's say. Now, if you make it bigger, if you make that directory bigger, you could increase the residency time for those entries. I had 5 minutes to go. But what's the likelihood of hitting a buffer in the local buffer pool that hasn't been referenced between 10 minutes and 30 minutes? As a percentage of all your get page requests, it might not be very high. So that's kind of the opposite of the sweet spot. It's the sour spot. Because you had it in the local buffer pool, but you lost it in the directory, in the group buffer pool, and it will cause a sync IO. So it's all related to these residency times. There's some health checks related to group buffer pool, directory reclaims. Those are the ones that I tend to see the most. And but I haven't seen failures due to inability to write to the group buffer pool, either the primary or the secondary. But those are just 3 metrics that you can monitor. And then here's a graph of showing when the directory reclaims were occurring for this one customer. I did not observe a spike in the sync IOs when this happened, though, so I wasn't really too concerned about that. You can get those. I've said this like 2 times already, so I'm going to skip that. There's also Rmf metrics that you can monitor, use to monitor the health of your system. And I didn't spend any time including charts, but there's the CPU utilization of the group buffer pool that you get from Rmf, not from DB2, but in Rmf. The hyperlink utilization, which is the path between the LPAR and the group buffer pool, and the actual response times for sending data to the group buffer pool or reading them back. Cast out I/O performance used to be one of the biggest problems with group buffer pools. But over the years, IBM has done such a good job of improving the I/O for things like Metro Mirror. And I have a chart later, I think, about it. I'm going to talk about it now. Back in 2016, IBM delivered the cast out accelerator in the DS8000 control units. DB2 cast out accelerator, it's called. And that's associated with Metro Mirror for replicating data. And it eliminated a lot of the cast out problems. And I'm wondering if Hitachi has implemented it yet. They usually copy IBM within 3 years. So by now, they probably have it. But that third vendor, they don't have it, I'm sure. So cast out used to be a problem. And one of the things that people used to argue, and people in my sphere still have differences of opinion about the burstiness of the I/O, the cast outs, I mean, as well as the deferred writes. Some people want to spread the writes across time uniformly as much as possible to avoid large spikes or bursts in the write activity. I have 2 minutes left. I'm not of that opinion anymore because it's all asynchronous I/O anyway, and I think the system can deal with spikes as long as it's asynchronous, and it is. But when you do have write I/O problems, usually because of mirroring at long distance. And if you want to avoid the burstiness, people set class T to a small value. And starting in version 11, you could, before version 11, the lowest you could set it to is 1% of your group buffer pool size. And now you can set it to an absolute number to get it really, really small to avoid burstiness. But the downside of setting class T too small is you could cause more I/Os, and I don't like that. Also in version 11, we implemented GPP write around so that when you have a batch job running or a utility batch inserts, I mean, or a utility, and sometimes it could flood the group buffer pool, and that used to be a big problem. Flooding the group buffer pool can cause an outage because you can no longer write data into the group buffer pool, and the only way to get out of that situation is by running the recovery utility, which will apply to log records, image copies and log records. With GPP write around now, though, DB2 detects that this was happening with the help of the group buffer pool facility, and it'll start to, these batch jobs, batch inserts and utilities will just write directly to DASD when it's in write around mode. Now, and then we'll just start using basically normal deferred write processing. Now, one of the problems, what's the downside of that? Well, when we're doing deferred writes, we're latching the pages that we're doing I/O for, write I/O. So you could get more latch contention. The other problem is if the write I/Os are too slow, we start filling up the local buffer pool with modified pages. Let me skip ahead here for a second. This tells you this is a graph that shows you the number or the percentage of active buffers that are, the percentage of buffers that are active, meaning they contain dirty pages, likely, or unreleased get pages, or prefetch IOs in progress. And in this customer has a very, very large buffer pool. And so even though he got into GBP write around in all these situations, the percentage of modified pages is really small. It's less than 1%. That's nothing to worry about. If it got up to, say, 30% or 50% or 90%, you got problems. So that's something to watch out for. Just make sure you have a lot of buffer pool, large local buffer pools. And there are statistics that show you when the GPP write-around is happening. I'm backing up now. More statistics that show where pages are being written from, which members are coming from, so you can kind of monitor the flow through the system. I mentioned Cast-Out Accelerator already, and I'm running out of time. I'm out of time. So in conclusion, make sure you have good performance monitoring tools that will allow you to visualize the data quickly so that you don't have to go searching for a needle in a haystack, and understand the actions that you need to take in order to solve response time issues and checking for health check failures. DB2 provides a rich set of statistics, but don't forget RMF, because he's got some additional statistics for you. There's lots and lots of data for you to look at. And these will improve your productivity. And I'm sorry I don't have any time left for questions, but I'll hang around here later for a while in case you have any. Thank you very much.